In this video, we're going to look at the experiment that kind of solidified the particle nature of photons, of light, called the photoelectric effect, which was actually explained by Albert Einstein. This is what he won the Nobel Prize for, the only thing he won the Nobel Prize for. He never won it for special relativity or general relativity. Nobel Prizes can be a little bit political, as we all know. We'll also look at the fact that photons can have momentum despite the fact that they have no mass, and then talk a little bit about what we call the dual nature of light, having both wave and particle properties. So the photoelectric effect was seen if you shine a light on a piece of metal, and this can be different types of metal all do this, whether it's copper or nickel or whatever. Some electrons will fly off of that metal in kind of random directions, but if you set things up right, you can capture some of those electrons into an electrical current, and then you can measure that current. And this was all well and exciting, but this experiment is famous because it gave us a way to distinguish between the wave theory of light and the particle theory of light. And that's always a big deal in physics. If you can find some situation where your two competing theories give you different predictions, then you just do the experiment and say, oh, looks like one of these was wrong. So let's look at the predictions to start off with. If you are shining light onto metal, you can vary a couple of things about that light. You can vary the color of the light or the frequency of the light, or you can also vary the intensity, which is just basically how bright the light is. If you've ever had dimming switches in your home, you can change the brightness of the lights without changing the color of the light. So those are kind of the two main things you can vary. And then we're interested in how varying those things might affect the number of electrons as measured by an electrical current through this little circuit here. So the wave theory would predict that the number of electrons coming off, the current here, and the energy of the electrons coming off should increase with intensity. So you turn the light up, you get more electrons flying off the metal. Sounds reasonable. But it would also predict that frequency does not affect the energy or the number of electrons coming off. Because in order to kick these guys off with a classical theory, that's what we call non-quantum theories, you can just keep adding energy as you keep adding more and more light, and more intense light has more energy, and so you'll be able to kick off more electrons regardless of the frequency of the light. If it's a particle theory, under this picture, light is a photon, and each electron gets kicked off by an individual photon. So increasing the intensity essentially increases the number of photons that are coming. So that will kick off more electrons, but it won't give them more energy. That would require, getting hit several times by several photons, which is not likely to happen. So intensity won't affect the energy, how fast these electrons are coming off, but it will affect how many. Okay, also the kinetic energy, or how fast these electrons are going, increases as you change the frequency of light, whereas here frequency would not matter at all. And there would also be a cutoff below which no electrons would be emitted. No matter how bright you make that light, if the frequency is too low, essentially the energy in these photons, in a single photon, is never going to be big enough, even if you got a whole bunch of photons coming in. So these two are kind of similar, and they contrast with this one, right? Frequency makes a difference if light is a particle. So let's see what happens. So here I have my wonderful little photoelectric setup. We've got a piece of metal here, and then we're going to change our light here, and then here's our circuit that the electrons can go through. So right now there's a bit of sodium right here. We could change it to zinc or copper, changes the color a bit. Let's leave it as sodium for now. And I'm going to shine some nice 450 nanometer blue light. Right now the intensity is 0, my light is off. And if we increase the intensity a bit, we get some electrons flying off. Now, both theories predicted that changing intensity will change the number of electrons coming off, right? And that's exactly what we see happening. As we get more intense, we get more electrons coming off. But the wave theory said as we get more intense light, I should get faster electrons coming off. And you'll notice these electrons here are not appreciably faster than these few electrons. Maybe it's too dim here. Than these few electrons coming off here. Okay, so that already is some evidence for the particle nature of light. And then the clincher is the wavelength. So if I lower the wavelength, I'll get to a point where I don't get any electrons coming off at all, regardless of if I turn this up to full intensity. That was a really slow electron. Okay, but even as we see with this lagging electron here, changing the frequency did affect the speed of the electrons coming off. Okay, so these electrons are a certain speed. As I go back to my blue light, you'll notice those electrons kind of catch up. And as I keep going up here, you don't need to use visible light for the photoelectric effect. You can use UV light. So these guys are really cruising, okay? So this experiment showed all of the predictions of the particle theory, that the changing frequency affects the energy of them, which the wave theory of light says it shouldn't. Changing the intensity just changes the number, but it doesn't change the energy. Okay, heading back. So just belaboring the point a little bit. Number of electrons, yes, that worked. Energy would increase, no, that didn't work. And all of these things were shown to be true. Another way to look at the photoelectric effect is the kinetic energy that the electrons are going to have. So this is the electron's kinetic energy. That's going to equal the energy of the photon that knocked that electron off, minus the work done to yank it out of the metal, because it's bound to that metal with electrostatic force. So it takes some work to pull it off. And if we rewrite this equation, we typically think about the minimum work required, because some electrons are held more tightly. They could be deeper in the metal or whatnot. So we call this the work function, and it differs from metal to metal. But it's essentially the minimum amount of work to remove an electron. So that's going to give us the maximum amount of kinetic energy that can come off. Now in that simulation, I had them all come out at the same energy for a given frequency, but in reality you'll have some faster and some slower. But we can measure the maximum kinetic energy by applying a voltage and seeing. That's why there was that battery in that picture. We can see when the electrons stop, and that's the way that we can measure this. Okay, then the energy of the photon is equal to HF. So here is our equation that we're going to be using for the photoelectric effect. And if you look at this, this is going to be a constant, and so H is a constant. So if we graph this, the kinetic energy should be linearly proportional to the frequency, and that's exactly what we see. We have a certain threshold frequency, a cutoff frequency, below which that frequency we don't get any electrons out, but that is even predicted by this equation, right? This is going to have a negative y-intercept over here, so that's going to be W naught down there. Okay, let's do an example with this. So if we want to know the maximum kinetic energy and speed of an electron ejected from a sodium surface, so a piece of sodium metal, whose work function is 2.28 electron volts. There's those electron volts again, we can convert those to joules, when illuminated by a 410 nanometer light. So first thing we're going to do is find the energy of those photons. Energy is HF, or it's also HC over lambda, and since we have lambda, we're going to use that version. So this was 6.63 times 10 to the negative 34th. C was 3 times 10 to the 8th. And then we're going to divide. You always want this to be in meters, so that's 410 times 10 to the negative 9th. Okay, and that works out to be 4.85 times 10 to the negative 19th joules of energy. And if we, sorry about that. And And here, if we want to go from joules to electron volts, we can divide by 1.6 times 10 to the negative 19th, and this works out to be 3.03 electron volts. So that is going to be the energy. We don't have the maximum kinetic energy yet, so to get that, we say the kinetic energy equals HF, which is the energy of the photon. I'll just write E photon here, minus the work function. Energy of the photon was 3.03, minus the work function was 2.28. By the way, if we had plugged in our wavelength and found something less than 2.28, which means if we would have had a larger wavelength, because that's a lower energy photon, then we would say the maximum kinetic energy is 0, because if this is below the work function, it's not like we get negative kinetic energy. Essentially, no electrons come off. Anyway, just finishing up the calculation right here, we get 0.75 electron volts. It's going to be the maximum kinetic energy of electrons ejected from the sodium. Now, if we want to find the speed, we actually have to convert this back to joules. I will spare you a bit of the shown work. So that is the number of joules corresponding to 0.75 electron volts, and we set that equal to 1/2 mv squared. They were electrons, so we're going to plug in the mass of an electron, 9.1 times 10 to the negative 31st, all of that times v squared. So we can solve for the speed of these electrons if we know their kinetic energy. It turns out that they are cooking right along at 5.1 times 10 to the 5th meters per second. Okay, some other implications of this. If our electrons, some other implications for light being a particle. Well, if it's a particle, it's going to be traveling at the speed of light, so we're probably going to want some relativistic equations. So, flashback to relativity. If you remember, relativistic momentum is gamma times mv. The total energy of a relativistic particle is gamma mc squared, and then if we just write out gamma, it looks like this. Now we can do some manipulation here. I won't talk you through all of this, but if you'd like to pause the video and think about it, feel free, and then you can ask me about it later. But if we square the total energy, we'll get this, and then we can do some manipulation, and we end up with this nice little expression here. E squared equals p squared c squared plus m squared c to the 4th, and because the mass of a photon is indeed 0, the rest mass, that part goes away, and we just have e squared equals p squared c squared, so we can take the square root of everything, and we get E equals pc, and if we rearrange that to solve for the momentum, we find that even though they don't have mass, photons do have momentum that is equal to the energy of the photon divided by the speed of light. And more fun with equations, we know the energy of a photon is hf, so we can relate that to the momentum of a photon. We also know that frequency is c over lambda, so if we plug that in for frequency here, then the c's cancel out and we get h over lambda is equal to the momentum of a photon. And a little example here, if we have a bunch of photons that are hitting a piece of paper, we're going to figure out the force, because if you have momentum and that momentum changes, that will exert a force. So massless particles, photons, can exert forces. As we'll see, they'll be pretty small. But to start out with, let's find the momentum of a single 500 nanometer photon. So in that case, whoa, what happened to my P there? The momentum equation that's going to be most useful is just h over lambda. H is 6.63 times 10 to the negative 34th over our wavelength. Again, we want this in meters, so times 10 to the negative 9th. And this gives us a whopping 1.3 times 10 to the negative 27th. And these have regular momentum units, either kilogram meters per second or Newton seconds, either way. So there is the momentum of a single photon. Now, if I want to know the force, if you remember some of your momentum equations, we said that change in momentum is equal to force, average force, times time. So if we rearrange this, we can say that the force is the change in momentum over time. Now here we don't want the change in momentum of a single particle, we want the change in momentum of all 10 to the 19th photons that are hitting this paper every second. And the final momentum, well, this is going to be final momentum minus initial momentum. Final momentum is 0 because we're assuming this thing is being absorbed and stopping. We're going to get a negative sign here, but we don't really care about that, so I'm just going to kind of forget about it. So the initial momentum, so n times initial momentum over t, n is 10 to the 19th. The initial momentum is just the momentum of a 500 nanometer photon, which is 1.3 times 10 to the negative 27th. You'll notice that the momentum of a photon just depends on its wavelength or frequency. It's always constant. You don't have faster photons or slower photons because they're always moving at the speed of light. So the momentum is always fixed for a given a photon of a given wavelength. Okay, and this was 10 to the 19th photons every second, so we just divide this by 1, and we get a big whopping force of 1.3 times 10 to the negative 8th newtons, which is why you can't push people around with flashlights. All right, now all of these wonderful things lead us to something known as wave-particle duality. If we think about when we studied light being a wave, right? And we said that it was kind of a hard thing to prove that it was a wave at first. People didn't believe that it was a wave because Newton said it was a particle. It turns out he was right, but not really for any correct reasons. So we had a number of experiments that finally convinced everybody that it was a wave, right? We showed that light can diffract, we showed that it would refract, we showed that there was interference, and the double slit experiment was kind of the nail in the coffin. Solid evidence that light is certainly behaving like a wave. And then now we've got our light is behaving like a particle. We've got the photoelectric effect is one of the, not photoelectric. Anyway, I'll stop there. Photoelectric effect. Black body radiation in general cannot be explained unless we say that the energy of light is quantized, which kind of goes along with the idea of it being a particle, so black body radiation. There's a number of other things that we haven't talked about. One of them is known as Compton scattering, which is basically light bouncing off particles and sending them in other directions. It's called the Compton effect. And we can see from those types of experiments that the amount of energy that those photons can impart has to be quantized as well. So what do we have going on here? Which one is it? Well, this kind of brings up a good philosophical discussion. We can't actually look at light. We can't freeze it, hold it in our hand, and look at it and say, oh look, it looks like a wave or it looks like a particle. So basically we make abstractions, we make analogies to things that we're used to in the macroscopic world. And so sometimes it does things that look like the things that waves do. So we say it must be a wave. Sometimes it does things that look like what we would expect a particle to do. So we say it must be a particle. What it actually is, who knows? It's some other entity. It just happens to exhibit the properties that these things exhibit in the macroscopic world. So this kind of shows the limitations of the models we can make to describe the unseen world, you can say. And this leads us to what we call complementarity. This Niels Bohr kind of came up with this idea. And he said that to explain a given experiment, you can describe light as a wave or a particle, but not both. Not both at the same time. It's one or the other. What it really is, who knows? Whether that question even makes sense, it's not really a scientific question, as long as we can explain. I guess it depends on what the goals of science are, but typically the goals of science are to have a model that fits the data, and these models fit the data. We just have to switch models depending on the experiment. So complementarity says that these two, the wave nature and the particle nature of light, complement each other, and together they give us a full description of what light does. So we can't picture what it actually is. We don't have kind of a unified single model for it, but that's the best we can do. So hooray for quantum mechanics. See you next time.